We will now do another example, and this is the same one that we did before in chapter 10, the last video, number 7 of chapter 10. This was the problem that we had done. We took a case of an object on a horizontal flat surface with friction and a pulley with the weight M1 attached here. M1 was falling down and it pulled this block towards the left, and we had the pulley not being massless, and therefore it has a moment of inertia, so T1 is not equal to T2. We solved that problem in that earlier chapter by using the energy conservation. So we said the change in the kinetic energy of number 1 and number 2 and the rotational kinetic energy of the pulley equals the change in the gravitational potential energy of number 1 and number 2, and this would be change would be 0, and we had a force pulling upwards, so that would be the work, external work, and the friction work. And we took the difference in the kinetic energies for final minus initial for number 1, for number 2, for the pulley, for the potential energy here the potential energy here, external work, and FD. We took some numbers and we plugged them in here, and we took F equal to 0 just to keep the problem somewhat simpler, and we got a final value of 4.2 meters per second. So now we'll solve the same problem with the same data by using this other method, and we will have the mass M2, force, normal force, friction, the weight, tension pulling this way and also pulling this way, and this is falling down with an acceleration A. So we'll use the sum of forces at MA, and the sum of torques equals I alpha. So that's somewhat different from what we had been doing earlier. We only had a sum of forces, now we also have sum of torques. So whenever anything is spinning, we need this equation. So we write F equals to MA, so from here we have the tension upwards, M1G downwards, so it's negative, it's accelerating downwards, we write M1 times A, and so T1 becomes, we bring this here, M1G minus M1A, and then we go for number 2, so we have T pulling to the left, T2, friction pulling to the right, so it's plus, and then F is broken up into two components, the Fx and the Fy. The Fx is going to pull to the right, and the result of this is that this object 2 is being accelerated towards the left because this is pulling it down. So we have two equations. The third equation is that the torque, and if you look at this part more in here, so the pulley is being pulled to the right by T2 and counterclockwise by T1, so the torque produced by T1 is T1 times R, which is positive because it's counterclockwise, and the torque produced by T2 is clockwise, so it's negative, T2R. R is the same for both, and that equals I alpha from this equation. So T1 we take from here, and T2 we take from here. T2 is going to be equal to friction, Fx, and M2A. So that becomes T2 times R. We'll again assume it's like a disk. The pulley is like a disk, so it's half mr square, and A alpha is A over R. Now we need to find the friction, which it's the same as before. Again, we'll have a normal force and a Fy upwards, Mg downwards. So we have normal upwards, Fy upwards, Mg downwards. So this becomes the normal force, and friction will be mu n. And as before, if we take the F equal to 0, so it's just simply M2G, and it comes out to 7.84 as before. Now we'll plug the F over here, but before we do that, we'll do some more algebra. So we can cancel this R with 1R, and then we have R, R, and R. We can cancel the 3 R's, and what we're left with is M1G minus M1A, and these three terms, but F is 0, so we have only the two terms, and M3A. Now we open this up, so it's M1G minus F, and M2 we take on the other side, and M1A we also take on the other side. So M1A comes here, M2A comes over here, and this is the third one. And then we factor out the A, and by some further algebra we get this equation. And now you can plug in the numbers. The M1 is 5 and 9.8, friction was 7.84, M1, M2, and half of M3, and that comes out to the acceleration is 2.94. And then we can plug that into the equations of motion, and this will be a constant acceleration, therefore we can use these. We plug them in here, and we take V initial as 0, we get 17.64, the square root is 4.20, the same as what we had before, which is what we should have got. So this is, let's say, the last example that we want to do. The other thing that's left in this chapter is a gyroscope, and I would suggest that you look at the video on gyroscope that's in the pre-class quiz. It's a pretty good one, and it covers most of what we want to do. Okay, thank you.